Hello everyone, my name is Maroun, and in this video I'll be presenting our paper towards dual issue single path code. Just a quick overview, I'll begin by giving some background information on single path code, then present the problem we were looking at, which is that it doesn't support Patmos's dual issue pipeline, which means single path code only produced one instructions at a time, while Patmos can execute two instructions at a time. Then we'll look at the specific contributions of our paper and some evaluations. So, a real-time system controls an environment by receiving data, processing them, and returning the results sufficiently quickly to affect the environment at that time. So if we, for example, take an autonomous car, we'd like for it to be able to look at it, what's in front of it, detect a person, and brake before it hits that person. So that puts some limitations on the programs it runs so that they finish their work before the car hits the person. So if we take an example program here, execution starts at the top with A, it runs through the various states of the program and then finishes in H. One example run through this program would be this one. Start at A, then go through B, D, E, G, and then finish in H. This is a very short program, but depending on the data that the program is analyzing, different execution paths will be taken. Here are two examples with various lengths. They, for example, loop a few more times. So the important question is, what is the worst case, what we call the worst case execution time of this program? And we need this to be able to build the car such that it can brake in time. And to find this worst case execution time, we have to analyze the program ahead of time. And this can be very computationally expensive, but also imprecise because of all the different paths through this program. So we have single path code that tries to remove, or it does remove, all data-dependent execution time variance, such that worst case execution time analysis becomes almost trivial to perform. Now there's a small caveat here, and that is that there are other sources of variance in a system, for example if it has caches, but single path code doesn't address them, and we won't address them anymore in this video either. So if we take a traditional program here, we can see a branching. Depending on an input value P, the program either goes from A to B and then to D, or from A to C and then to D. So if B and C have different execution times, depending on which one of them is taken at a given run of the program, the execution time will differ. So single path code tries to make execution time constant regardless of input data. And it does so using predication. A predicated instruction is either turned on or off depending on some value, and if it's turned on, it's the usual instruction is run as usual, but if it's turned off, disabled, then it will have no effect. For example, it won't write anything to memory, it won't have any effect on registers in the CPU, but it will run, take exactly the same amount of time to run. So in our example, when we're running A, we then run B if P is true. We can run B completely normally, but by the time we reach C, P is not false since it's true, and all instructions in C are turned off and have no effect, but they take the same amount of time. And we finish with D here. So every run of the single path version of this code takes exactly the same amount of time to execute. We need to do this also for loops in a program, because for various data, the number of iterations the loop is run differs, and this can affect the execution time. So what single path code does is always run a loop the maximum number of iterations that it could have. And this is so that the execution time is the same either way. But for any extraneous iterations, the body of the loop is turned off. Now this is easier to show with an example. So we'll use this example where we, for a specific run, we need to iterate in the loop twice, but the maximum possible run is 4 times. So in the beginning, the body of the loop is turned on in B and C, and when we reach its end, we'll simply loop back to the beginning. So we start at I0, Then after one loop, I becomes 1, but we still need another loop to process our data. So we run it another time, but now I is 2. So we've run the required number of times, but we haven't reached our maximum number, which is 4. So what we do is we turn off B and C, but run the loop again. The loop has no effect, but its execution time is still there to make it constant in the end. So we run until I is 3. We still need one more. And when I is 4, we have now run the loop 4 times. The last 2, of course, did absolutely nothing. But now we have the constant number of iterations we need, and we can exit the loop and finish with D. And so this program will always have the same execution time. So we have Patmos, and it is a processor specifically designed for real-time systems. What it does is reduce worst-case execution time of instructions instead of the average case execution time, which is what conventional processors usually do. It also specifically supports SinglePath code by having these predicated instructions that can be turned on and off. And lastly, it is a very long instruction word architecture. And what that means is that instructions come in bundles of 2 that can be executed at the same time in the parser. They can also come in bundles of 1, which is exactly our problem. Before this work, the SinglePath code generator would only produce 1 instruction at a time and basically waste the second instruction, so wasting half of the processor. So our contribution is a description of a dual issue SinglePath generator with bundling support. And bundling is taking 2 blocks of instructions and then bundling their instructions together so that both bundles are executed at the same time. The first block will get its instructions executed on the first issue slot on the processor, and the second block will get the second issue slot. Now, simply bundling them together isn't as simple because not all instructions can be in both issue slots. For example, loads have to be in the first issue slot, so if both blocks have loads in the same position, then they need to be interleaved to execute correctly. So we also have an implementation of this generator for the Patmos compiler, and in the end we evaluate on its performance. So in short, what we have done here is add a bundling step to the SinglePath code generator. And this bundling step specifically takes these 2 blocks and bundles them. And it happens in 2 steps. First, find block pair, which finds 2 blocks that we can bundle together. And then bundle block pair takes these 2 blocks and actually bundles them together, putting the instructions in the right place. Now, there are some requirements on whether 2 blocks can be bundled together. The first one is non-equivalence. If one block is enabled, its instructions are enabled, then the other block must be disabled at all times, or the other way around. If the second one is enabled, then the first one must be disabled. And this is so that they don't interfere with each other. The second one is non-domination. That is simply one block cannot be dependent on another block for its execution, because when we then bundle them together, we have then changed the semantics of the program. The third requirement is also that all blocks must come from the same loop, because they need to be run specific number of iterations, and if they come from different loops, they might have different number of iterations, and so we change the semantics if we bundle 2 blocks from different loops. So what we have done is implement a very naive bundling strategy, just to see that we can produce dual issue SinglePath code. How the naive algorithm works is it goes through all blocks in a loop, then it looks at the children of this block, and if it has 2 children, meaning there is a branch, then it sees if these 2 children adhere to the requirements and can be bundled, and if it does, and if they adhere, it does so. We check all blocks in the loop for whether their children can be bundled until we run out of blocks. And we do the same for all other loops in the function, and when we don't have any more loops left, we finish. So what does this result in? So this is the traditional example we have on the left. This is the SinglePath code with no bundling. You can see how the states of the program have kind of been serialized, but we can still see the loops are there between E and B and F loops on its own. But using our bundling strategy, we can figure out that C and D can be bundled together because only one of them is enabled when the other one is disabled. And so our algorithm bundles them into one block, running them on the processor at the same time. So what does this result in? We've measured the number of cycles programs take to execute. We've used programs from the Tackle benchmark, which is a benchmark for real-time systems, try to simulate real-time workloads. And this benchmark has a lot of programs, but only actually 9 of them managed to, where our compiler managed to produce single-path code for them. The compiler is sadly not in a good enough state to produce single-path code for the rest of the programs. What we see here is actually only 4 of those programs because the bundling step didn't produce any improvements or changes in the instructions for 5 of the 9 programs. So what we're seeing here is the 4 programs that actually had any effect when bundling was enabled. What we can see in the first row is the number of cycles the program needed to run when it didn't have any bundling. The second row is when bundling was enabled, and we can see that the number of cycles is reduced. The third row is just the difference between the first 2, and the fourth row is the difference in performance in percentages. So for example, for count negative, the third column, it had a 2% performance increase, so not very much. So we try to evaluate how that happened, what is the algorithm doing. So what we can see here is all 9 programs. And from on the pair bundled column, you can see that the last 5 have zeros, and this means that no bundling happened. It didn't find any pairs of blocks to bundle together. For the first 4, what we can see here is that it didn't really work that well. For example, for B-sort, out of the 17 blocks that were there before bundling, only 1 pair was found and merged. But as you can see on the right, 7 pairs were rejected, so it found that it couldn't merge them. So what we can see is that this algorithm is not very good at finding blocks to merge. But maybe our performance could still have been better if the part of the algorithm that actually merges blocks could have done better. So this table here shows the effects on instructions in the programs that received bundling. And what we can see here is in the before column, the number of instructions in the program before any bundling happened. The second column is the number of instruction pairs that were bundled together into one bundle. And the third, the last column, is the number of instruction pairs that couldn't be bundled because, for example, they were both loads, so they had to be interleaved instead. And we can see that the last column here is all zeros, so there were no inefficiencies in having to interleave any instructions. So basically our algorithm is not very good at finding blocks to bundle. So in conclusion, we have an automatic generator for dual issue single path code now, which supports a general bundling algorithm. That means that we can in the future work on finding a better bundling algorithm without having to change too much in the compiler. We have an implementation of this algorithm in the Patmos compiler, and we've shown that there is performance potential to be had from introducing bundling into single path code. So for example, for the count negative program, we only saw a 2% performance increase, but that is only based on bundling 2 instructions. So that is very an optimistic result, because if we can just bundle them better, then we will probably have a very good performance increase. So that would be for future work. I'd like to now thank you for listening and take any of your questions.